Step 3, we now use Faraday's law to find the induced EMF in the secondary and the induced current in the secondary. So we state that our induced EMF, which could be a function of time, will be equal to our induced current in the secondary, which could be a function of time, times the total resistance of this secondary loop. We could sort of schematically represent the resistance of that entire loop of wire with like one representative resistor over here. So let's say this is total resistance capital R for the whole rectangular wire loop. That's this resistance capital R right there. Is equal to the opposite of the time derivative of our magnetic flux through that rectangular loop. Okay, so from step 2, we've got our expression for the magnetic flux through that rectangular loop. And so we find that the current in the secondary, the induced current in the secondary as a function of time, will be equal to the opposite of, and our expression for the phi b was as follows. We have a mu naught over 2 pi. We have, here's the 1 over R factor when I divide through both sides here by the total resistance R, times the current in the primary, which is a function of time, times these geometric factors, the width of the loop and the log of the ratio of the distances of the near and far sides of the loop. Okay, I think we've got it. This is what we've been looking for. Our expression for the induced current in the secondary as a function of time, as it depends on the time variance of the current in the primary. Oh my gosh, but I forgot I forgot our time derivative here, ddt of all of this. Okay, so we need that time derivative in here. Let's look through and find the things that are functions of time. It looks like just I1 is our function of time. Here, let's say that our secondary loop is fixed in place. So we're going to let B and A be time independent. So note here, for the moment, A and B are fixed and not time dependent. We're nailing our secondary loop down and not allowing it to move. That way, when I take the time derivative, it only acts on this, the only time dependent part. So I forgot to write it in here. This is d dt of I1 right there. So that is the only thing that has a time dependence on, so that's what gets that time derivative. Okay, just double checking to make sure I've got this right. All right, I think we've got it. So let's have a look at the signs and directions here. What does this negative mean, for instance? Okay, so looking at our current loop here, the DS's, that defines the direction of a positive current through I2. It's another function of these DS's here. So an I2 that goes in the direction of the DS's would be considered a positive I2. So a counterclockwise I2 is positive. Let's see why that is. Going back to this other form of Faraday's law, if E dot ds equals IR, this would be our induced current I2, that current and the current density J, based on this equation, is in the same direction as the induced electric field. So this is the E field that is the induced E field that's driving our induced current here. So they're in the same direction. So if E dot ds is greater than 0, then that means this I here will be greater than 0. That's why we're saying that if the current is in the direction of ds, then it's positive. Likewise, if E dot ds is negative, then I here is negative. So if the current is opposite ds, that's going to be considered a negative current. Okay, so I've here drawn the direction of an I2 that would be considered a positive I2. Let's look at this equation. What we see here is that if this is a positive I1, and if, for example, it were increasing with time, so if I1 were getting stronger, di1 dt would be positive. These other terms are all positive, but there's a negative right there. So if I1 were getting stronger, this would be positive, and I2 would be negative. So if I1 were getting stronger, that implies that I2 would be negative. That is, I2 would be opposite the direction of ds's. I2 would be going clockwise instead, as we've already worked out before. So if I1 is increasing with time, I2 would be clockwise. I2 would be a negative current. Likewise, if I1 were decreasing with time, if I1 were this way but getting weaker, then di1 dt would be negative times this negative would make I2 positive. So if I1 were decreasing with time, then I2 would be positive. I2 would be running counterclockwise in the same direction as ds, as my blue arrows here are showing. All right, so that was our initial goal, but I would like to take this a step further. Now that we recognize that we've got current running in our secondary loop, clockwise or counterclockwise, depending on whether I1 is increasing or decreasing. Now that we've got current running in the secondary loop, and that secondary loop is immersed in this magnetic field B1 that's created by our primary wire, now these current carrying wires in an external magnetic field are going to be feeling electromagnetic forces, Philb type forces. Let's have a look at them. So two instances here, two examples to consider. Suppose I1 is this way, and we call that positive, and it's increasing with time. Then we know that I2 will be clockwise. So I2 will be in these directions. It'll, in general, be a function of time since I1 is a function of time. Okay, so if I1 is increasing, I2 will be going in these directions. Now there are going to be magnetic, or not magnetic forces, but let's say electromagnetic forces, Philb type forces on these segments. F equals IL cross B. So if we do I cross B, B's out of the page here on this lower section of wire here, that IL cross B, my thumb is pointing up, this would feel a force pointing away from the primary wire. Likewise, the top section, IL cross B, I cross with B, thumb points down. This would feel a force pointing down. But note, the magnetic field up here is going to be weaker than the magnetic field down here, since this side is closer to the primary wire. So the downward force on this top section of wire will be smaller in magnitude than the upward force on this bottom section of wire. So we've got a net force in the positive direction on our loop here. Let's look at the two side segments for a moment. IL cross B again. So IL cross with B, thumb to the right. This would feel a force that way. This side, IL cross B, thumb to the left, would feel a force that way. And by symmetry, those two forces should cancel each other out. So in our loop here, it looks like we would get a net force pointing away from the wire, from the primary. This loop, as I1 increases with time, this loop is going to be pushed away from the primary. It'll be forced away as long as I1 is increasing, which makes sense if you focus on these two wires here, the primary and the nearest part of the secondary. You've got currents pointing in opposite directions, and we know parallel wires carrying currents in opposite directions repel each other. So this case, our wire loop would start accelerating away from the primary. If, on the other hand, I1 were decreasing with time, I would like you to work out the directions of those forces here. Take a moment, pause the video. Got it? Okay. In this case, we worked out if I1 were decreasing with time, then this outward flux would be diminishing with time. We would be needing to add more outward flux through our loop here, and thus we would get a counterclockwise induced current. So it would add its own secondary B field pointing outwards through that loop to replenish the flux through that loop that we're losing. So here would be our I2 as a function of time in this case. And let's look at those filled forces. On the bottom section, we would have I2, IL crossed with B, so a force downward. Top section, IL cross B, force upwards. Side sections, IL cross B, force to the left. This section, IL cross B, force to the right. So if the current in our primary is decreasing with time, then that flips the directions of all these electromagnetic forces on the sections of our secondary wire. We see the left and right segments, those forces would cancel each other out. But these up and down forces do not cancel each other out because, once again, the magnetic field nearer the primary is stronger than the magnetic field far away from the primary. And since the electromagnetic force, the filled force, is directly proportional to the field strength, this force on this segment will be stronger than this force on that segment. So this wire, this secondary loop in this case, would be feeling a net force towards the primary. So as we turned down the current in the primary, as we diminished that current, our secondary would be pulled in towards it. And again, that makes sense. If we look at the nearest segment of wire to the primary, we've got two parallel wires carrying current in the same direction, and we know that those two wires would attract each other. So looking ahead here, we note that by controlling I1, by increasing it, we can push this loop away. By decreasing it, we'll pull that loop towards us, and we'll come back to that point at the end. Let's pause here.